Welcome to lecture 34. In the last class, we have studied Bishop's simplified method. It is similar to ordinary method except that we consider normal interslice forces, that is forces normal to the interslice on either side, vertical equilibrium, force equilibrium, and then of course the moment equilibrium from which you get the factor of safety, which is an iterative process. So for each trial circle you have to do a number of ones. This what we discussed was a simple static case. Nowadays we are more concerned about the effect of earthquake. So if this slope is in seismic area of say earthquakes of serious magnitude can occur. Let's say you are looking at Garhwal, Himachal Pradesh, Kumaon, Kashmir, northeast, or even some in the south, for example, Jabalpur, and in the Kutch region, the earthquake intensity can be very high. If I look at the Indian map, a very good way of writing it, you have very high earthquakes in this region, northeast, these are the Himalayas. And the country, if you look at the seismic map, we have only zone 2 and 3 here, but these can be 4, 5, very high intensities. If an earthquake occurs, you know that the earth shakes a lot and this energy is transmitted. So the way to handle in a very simple form would be that when I look at the force due to gravity, its vertical force Wi on the ith slice, what we say is because of an earthquake, you will have a horizontal force which is equal to Wi into alpha I. Alpha I is the seismic coefficient. I'm sorry, alpha H, not I, alpha H. Alpha H is the proportion of the gravity force that is likely to cause a horizontal additional force on the slice. And when you look at the center, now you will realize that not only the force is giving you an anti-clockwise movement, but even the earthquake force gives you an additional horizontal component and the anti-clockwise movement. And that is the reason why under earthquakes the slopes fail, you have an additional dynamic force, though we consider as a pseudo static force. During an earthquake, the slope and the slices could be subjected to additional force, which is considered to be in the horizontal direction because the earth is going to shake horizontally, and that is transmitted. It's a component of the gravity force, and that component is called the horizontal component of seismic coefficient alpha H. So when you now calculate the factor of safety, you have to take the component alpha H into account. So all your expressions will now have an additional term which will cause instability. So the term becomes added in the denominator. So if I write that expression, if you remember we wrote Fs by the Bishop's method is equal to sigma I is equal to 1 to n Ci Bi or C by Fs if you want to, plus Wi tan phi by m alpha I divided by I going from 1 to n Wi sin alpha I plus I have to consider this distance Zi Wi into alpha H. The seismic force will also add up to the disturbing or activating force causing instability, so the denominator becomes significant. And once it becomes, so Fs under earthquake conditions will be much less than Fs under simple static. That is very important to consider. Please remember that when an earthquake occurs, you find that the seismic coefficient will be very small. But luckily, we don't have to satisfy a very high value. If this is around 1.5 for static, should be greater than 1.5. To be safe, you may sometimes say 1.75 or even 2, but code says 1.5 is enough. Under earthquake conditions, we are satisfied if it is 1.3. Sometimes we even go to 1.2 if it is a remote area and you are not worried about it. But the only change you have to make is consider an earthquake force in the horizontal direction, and that force is a fraction. For example, if you are in zone 3, this may be around 0.8, whereas if it is in zone 3, in zone 4, maybe it's around 0.12, and in zone 4 it may be 1.7 to around 0.2, very high values. So depending on the code, you take appropriate value and then substitute that in our analysis. That gives rise to a lower factor of safety, and that should be greater than at least 1.3 for the slope to be stable. If it is not, you are expecting some trouble, so we had to make it flatter to get a minimum factor of safety of 1.3 under earthquake conditions and more than 1.5 under dynamic conditions. So this is how we use the method of slices. Just want to introduce to you some simple approaches. If the soil is homogeneous and clay, then we have these charts available which you can use without going through all this. So slopes with homogeneous clays, then I don't need to do all this because fortunately those charts are already available. We have a clay with just simply undrained strength Cu, and the friction angle or angular shear resistance phi u is 0. It's an undrained condition. In this case, we look at the possible solutions, which are if the failure surface goes through the toe, it's called the toe failure. The failure surface pretty close here and goes to the toe of the slope, whereas if it goes into the soil below, this is called a base failure. And sometimes you will have a very shallow failure. This is called the simply slope failure. There is another possibility that if the slope is on a hard surface, the failure surface will be tangential and may not exactly go through the toe. It will be slightly above the toe. But even here, we call it as a toe failure. So let's look at, mostly we look at, this is very unlikely in a homogeneous slope because this height is much smaller, h1 compared to say h. So obviously this will be more critical than the shallow one. So we normally consider ours only toe or base failures. In this case, it becomes very easy to estimate the factor of safety because if you look at the slides, we only have cohesion, so I can easily find out the moment resistance. Let us say you are looking at this failure surface and the weight is W, x bar, and what you find is the strength mobilized along the arc of the circle. So if this intended angle or internal angle is theta, this is r, then factor of safety is equal to Cu r into theta and into r. R theta gives me the arc length into Cu by r square divided by W into x. And you can divide into number of slices or use simple geometry to find out what can be the summation of these moments causing sliding. So instead of, if I know the geometry, I'll take the centroid and look at xi, which is what has been done by Taylor and others. And what they found was by defining a stability number ns, which is equal to C design by gamma into H. The only terms are, and C design is equal to Cu by factor of safety. I assume that full strength is not mobilized, but I only want to reduce by factor of 1.5 or 2, and then I find out C mobilized or C design. Then I get what is called a stability number. What, fortunately for us, people have studied and found out the minimum value of the factor of safety. So we have a chart which gives me stability number ns goes from, let us say, 0 to 0.3, and I have the slope angle beta here, and I find that the stability number decreases as the slope angle also decreases. Or if I look at beta increasing, stability number increases. So if I know the properties, I can calculate the stability number, and once I get this, I can find out stability number is equal to ns. Let us say corresponding to something like 40-degree slope, I get ns is equal to 0.15. Then ns is equal to 0.15 is equal to CD by into gamma h. Or I can find out gamma h is equal to CD by gamma into stability number. So this is the maximum height you can provide, and the real height in this case, factor of safety would be equal to h from the chart divided by your design. So that gives me the factor of safety. Let us say from here you got h is equal to 15 meters, and if you are only providing 10, you say that I get a factor of safety of 1.5. And this curve is for this term d, the depth of the hard layer. This is d times h. So d is equal to infinity. That means the hard layer is fairly below. But if you have at a finite depth, then you have stability number coming, let's say 1, 2, 5, 10, etc. It becomes stability number curves are below. Other thing I would like you to know is that if beta is greater than 53 degrees, steep slopes, we get slope failure or toe failure. And if beta is less than 53 degrees, we will get base failure. That means flatter slopes, the failure surface goes below the bottom of the slope, below the toe, and you will get this. So there is a transition here, and for steeper slopes you get the factor of safety, I mean the failure is only through the toe. Now the same thing, this chart has been extended by Taylor for seepage soil. Suppose I have the slope, again I look at the failure surface, this is the center. So now if I look at the force, the normal component is here, and if I now look at the frictional component, this is Wi, Ni, the frictional component is equal to Ni tan phi. So the resultant would be inclined at an angle phi. Please note that the resultant of a horizontal force N tan I and a normal force Ni will be inclined at an angle phi. So what Taylor said was, if I take a friction circle, he calls this, the resultant R is tangential to the friction circle whose radius is equal to R sin phi. I'm sorry, R tan phi. And so based on this, he could calculate the factors of safety. And so in all the books you will find very easily charts which will give you as a function of C and phi. The stability number Ns against, let's say, beta again. Now let me say this time we are plotting 0 to here. So the stability curves would be something like that. Phi is equal to 5 degrees, 10 degrees, 15, 20, and 20. So if you know C and phi of the soil and you know the friction angle, you go from here, get the stability number, which is again same as before, C by gamma H. And I can say, if you want to put in a factor of safety, so again factor of safety will be equal to C by gamma H into NS. Straight away you can find out. So using stability number, you can calculate the factor of safety using charts only for homogeneous soils. Now I am talking not clays, homogeneous soils. So the soil has both cohesion and angular shearing resistance. Of course, gamma is always there. People have even tried to include the port water pressure effect in terms of a coefficient RU, but that I would leave it at stage. What we will try to do now would be look at not natural slopes, but man-made slopes. We were looking till now about only the natural slope. Now look at, there are two kinds here. One is at the dam. Sometimes we call them as embankment dams. And the second would be highway and railway embankment. This is a very important topic. You would like to build an at the dam so that you can store water on one side. This is the reservoir and this is the downstream side. You may provide a filter, whatever it is. How do I check whether the dam is stable or not? So this should be what you have to do for at the dams, and these are all compacted by a geotechnical engineer designing the cross section, the material, etc. But what should be the slope? So we have what you can call upstream slope and downstream slope. They may not be same. The slopes can be different for the simple reason here you have water which is in a way supporting the slope, but if I look at the downstream slope, you have seepage going towards the downstream one. So when you compact it, you have to first find out gamma dry maximum and optimum moisture content, and then you specify to the contractor how constructed in the field. Each layer of 300 or 500 millimeters with a heavy roller, you compact it and then build up the dam. Now this height can vary depending upon the dam, and we have the largest one, the Theri Dam in India. It is about 265 meters, very high dam. Most others, like for example the Pochampad, etc., they are smaller, about 100, 150. So we have very high dams and you have to make sure the dam slopes are safe. There are three situations which are possible. One is called end of construction. Second is what you call steady seepage, steady condition. Third is called sudden drawdown. Let's look at these possible cases. Usually we build most dams at a water content of OMC plus or minus 2%, and if you expect cracking, better to go for the higher one. If the soil becomes more plastic, so you have slightly on the higher side, particularly for clays, it's easy to construct. And if you remember our water content versus gamma dry, you get a graph of this kind. This is OMC and this is called zero air voids line, which means this is 100% saturated. So if you go slightly to the right here, we are close to saturation. So when we compact it and do not give enough time, there is a possibility of port pressure generated. You see, you have started here and this is the dam and you are constructing in layers. So each time you are adding some weight. So when you add weight, from consolidation theory, initially all the gravity stresses go into the pore pressure, but luckily in most dams degree of saturation is less than 100%. So the pore pressure parameter B is less than 1. This is the Skempton pore pressure parameter. Beta could be less, but the fact that you may have some pore pressure at different places during compaction. So you have built up at the dam to a height of, let us say, 60 meters. So 60 meters of gravity load is acting of different intensities, of course, at different depths. So when I try to find out the factor of safety, when I look at the weight here, I need also to find out the pore pressure, because the strength mobilized is a function of pore pressure. And what we normally say is that it's very difficult to measure the pore pressure in a partially saturated soil, because we said the degree of saturation is less than 100%. So to measure pore pressure is difficult, so we define what is called as pore pressure coefficient, that is equal to U by the sigma. If the gravity weight is sigma, pore pressure is a fraction. And this RU can be, if it is 0, no pore pressure. If it is 1, it is completely undrained. We normally work in the range of 0.4 to 0.6 and say the pore pressures are about 40 to 50, 60% of the weight, and then you put that in our stability calculations. You remember we were saying in order to calculate the factor of safety, the resistive moment is calculated. In the numerator, you say C into the width plus W minus R times W. So I can simply say the vertical force into 1 minus RU. That into tan phi divided by, as usual, the other one, W sine, I think here I have to put cos, and tan phi is sine alpha I going from 1 to n. So here you have to take care of the pore pressure depending on the situation. Now I would like you to remember the climatic conditions. If you are building this dam in summer, the chances are the water will evaporate fast, so RU can be maybe something like 0.1, 0.2. But in the rainy season, as you are constructing, the water gets saturated. And if you try to build it up, RU can be very high. So that is why we take somewhere around 0.5 to 0.6. So as you construct it, the worst situation is end of construction. The full dam is constructed and you assume the pore pressure is proportional to the total weight acting on each slice corresponding to that depth, and that will be the most critical one. So you get factor of safety 1, first case. This should be greater than 1.5. So for an earth dam, you please check, if you are designing one, what will be the factor of safety at the end of construction, both for upstream and downstream. If there are different slopes, let's say this is 2:1, whereas this may be 2.5:1. So if of course if it is safe with 2:1, it will be safe against 2.5:1. Whichever is steeper, use that value. The second most critical condition is steady seepage. Then we look at the downstream slope. Then the critical one is the downstream slope. The earth dam has been constructed and the water is being stored. So this is the full reservoir level. And here is the downstream side. Maybe you provided a filter. You remember in our chapter 3, 4, we looked at seepage and we said we do not want the phreatic surface to go to the downstream side. If I do that now, the top phreatic surface is somewhere here. This is the downstream slope and this is our flow net for the steady seepage condition. So we say that equilibrium is attained. There is a continuous flow. Possibly, if the foundation is also pervious, you may have flow lines coming and daylighting here. So that kind of thing. But we are interested in stability of the downstream slope. So what we then do is take the center here, look at the arc of a circle, and suppose I have a slice here, look at the equipotential line. Corresponding to this, the pore pressure is equal to this height. For each slice through the bottom, this is the downstream slope, and here is the, from here I draw the equipotential line, and if it is the phreatic surface, this height HPI I have to find out, and the pore pressure at the base is given by the height of the phreatic surface for the equipotential line that is passing through the base. So now I have to consider pore pressures. Again, as I said, Wi minus pore pressure, which is equal to Ui, and Ui is equal to gamma W into HPI. So for each slice, you have to find out what will be the pore pressure at the base of the slice. In the steady seepage condition, we like to find out, first draw the profile of the dam, draw the flow net. So you need to draw flow net. And then you draw the trial arc, and for each trial arc, you have to find out what is the pore pressure at the base of the slice. And you correct for the normal force, weight minus pore pressure, and that will give me the effective thing, and in terms of that, tan phi gives me the frictional component. So for the downstream side, you have to include the flow net and calculate the factor of safety. This usually is also a critical one. The third most important one is if there was a dam break, or because of some reason the dam fails, reservoir is here and it is a filter, so the steady seepage is established. We have a steady seepage condition. Let's say the dam is very long and there is a huge flood, and you expect that maybe the dam is going to fail, or maybe it reaches a critical condition. Then what they do is, from the spillway they remove the water, and this water level comes down. So the drawdown is what you call sudden. There are situations where if the engineers find that the flow is so high the dam may fail, then they try to empty, or for some reason there is a break, there is a failure, in which case the water level will come down very fast. That is called the sudden drawdown condition. In this case, it is the upstream slope. You have seen that the flow lines and the equipotential lines are as follows. Now, in the normal situation, the weight of water is going to act normal to the upstream slope because it's a gravity force, so the stability is very high. Now, if you remove this weight, let us say the water level has come down here. The full reservoir is here, and for some reason the reservoir is emptied. And if this is done within 1 or 2 days, you find that the time is not enough for the pore pressures to be dissipated. So if I now check the stability, I find the pore pressures here are very high, because you see that seepage line, phreatic line is very high, and the pore pressures on the upstream side can be very, very large. If that happens, the factor of safety for sudden drawdown, the third case, could be low. So when you design at the dam, you design for the 3 conditions: end of construction, both slopes, and whichever is steeper will be the critical one. Then the steady seepage condition, it's generally the downstream. And if you find the factor of safety is low, you have to increase the filter, either take it inside, put a vertical chimney, or do something so that the factor of safety on the downstream slope is as per the required design. The third most critical one is when, in case the reservoir level falls down rapidly for some reason, then the upstream slope becomes critical, and then you have to take care of that. So these are the three checks we do for earth dams, which are constructed by men, or engineers, so that we can check for the constructed dam. The last type of embankments are, we are nowadays constructing embankments for railways and highways. So here you can have a road or a railway track. You have to check for the slopes here. And here we talk of two: normal embankments on fairly solid ground and embankments on soft ground. This is predominantly true in all coastal areas where you have marine clays, which are very soft. Again, we like to look at the soil here, determine its gamma dry maximum, optimum moisture content, determine the C and Phi of the soil. In the laboratory, using one of the triaxial tests, you have to do either undrained triaxial, consolidated undrained, and get C and Phi, and then check the factor of safety for the slopes here. If you are constructing it, usually the upstream and downstream slopes are same because there is no water now. The difference between an earth dam and an ordinary embankment is there is no water at all. So in this case, we try to get the factor of safety based on the type of soil we have. So you have to generally look at type of soil. If you can, prefer a granular material. And the slopes can vary from 1.5 H to 1 vertical to about 2.5 H to 1 vertical. This is a relatively steep slope, and this is relatively flat slope. You do not want to waste money, so the steeper the slope, the more economical it is. If the embankment is in the interior, let's say around Hyderabad, Guntur, Vijayawada, etc., there is no problem because the ground is generally really strong. But if you are building these same embankments for highways and railways in the coastal areas, what you find is the embankment may be a strong material, but the foundation is weak. This is the embankment, but you have a soft soil. We have serious problem in coastal areas, as I said. The strength of this soil can be as low as 10 kPa or even smaller. So it's like trying to put in a heavy load on top. So when I do this analysis, I'll have to worry about failure now. And here I had to use Cu of foundation soil, and this is C and Phi of the embankment. So when I look at the failure surface, you find you have two different types of material. A very soft material here and relatively strong material. And this has been a problem, for example, in New Bombay, Konkan Railway, Visakhapatnam, etc. When they built embankments in Visakhapatnam, there was in the port area even a 2.5 meter embankment, very small one, failed because soil could not withstand. So we'll have to modify that. So when you are designing embankments, you have to look at the foundation properties in case of soft soils. And what do? You have to find out the undrained strength of the ground and put the embankment, do the same stability analysis as before, but when you do this arc, the part which is below the embankment in natural ground has a different Cu. So if you are now looking at the properties, this range below the ground, use the CO, the foundation soil, and for the arc which is within the embankment, you have to use C and Phi of the embankment material. So this again is done usually through a software, and we try to estimate the factors of safety. There are different modes of failure for embankment on soft ground. I'll show you through my PowerPoint presentation.